There is no doubt that space is quite vast, especially for us humans, who are smaller than any atomic particle in comparison to this infinite universe. However, our curiosity always drives us to seek the boundaries of the universe. Now, the universe might not have boundaries, but we humans do have boundaries within this universe, or perhaps I should say there are many boundaries. One of these boundaries is represented by the cosmic microwave background radiation, CMB, located at a distance of 46.5 billion light-years from Earth, which is currently the absolute limit of the observable universe, beyond which we have not yet been able to see anything. We are able to see it because the photons from the CMB have entered the Hubble sphere, which extends for a radius of about 14 billion light-years around the Earth in the young universe. The photons that will not be able to win this race will never be able to reach Earth in the future. I know, there might be a bit of confusion here, given that the radius of the Hubble sphere is about 14 billion light-years, beyond which we will never be able to see light photons. So, how have we captured the CMB coming from 46.5 billion light-years away? Welcome to our channel. Today we will clarify all the concepts of the horizons of the universe for you, along with understanding the absolute limit for humans in the universe, beyond which we will never be able to see, no matter how long we wait, even if we wait an infinite amount of time or build telescopes of any size. As we know, photons travel in the universe at the speed of light. Even though it is the fastest speed in the universe, it still takes a long time to travel from one object to another. This is why, whenever we observe an object in space, we are actually observing a past version of that object due to the time taken by light to travel. For example, when you look at the moon in the night sky, you are actually seeing its version from 1.3 seconds in the past and the version of the sun from almost 8 minutes in the past. Additionally, the stars you see in the night sky, based on their distance from Earth, are actually versions that are many hundreds or thousands of years old. Through technology, we have been able to observe further into the past. That is why the James Webb Space Telescope, which is currently the most advanced telescope for humans, provides us with the ability to see objects present in the universe billions of light-years away, in a clear and detailed manner. James Webb has captured images of galaxies formed from the oldest light in the young universe. If viewed this way, we can divide the light coming from different distances in the universe into separate spherical shells, where the outermost layer of this imaginary spherical shell will represent the absolute Big Bang. Within it, there will be the particle horizon, which is currently equivalent to the observable universe, extending up to a diameter of 93 billion light-years. Next comes the Hubble sphere, covering a diameter of almost 28 billion light-years. Now, starting from the particle horizon, there is the absolute limit of the universe beyond which any particle can reach Earth. This limit is quite close to the Big Bang in mathematical terms, but so far, we have not been able to measure the particle horizon precisely. So far, we have only been able to capture the CMB radiation, which is located 46.5 billion light-years away from Earth. Therefore, the particle horizon is considered limited to that distance. However, in the future, it might extend further, especially when we capture those neutrinos beyond the CMB radiation, which have already entered our Hubble sphere, passing through the CMB plasma in the early universe. When these neutrinos arrive from beyond today's observable universe, we will be able to observe the Big Bang from a more detailed perspective through them. But for this, we will have to wait a little longer, maybe a few billion years. For humans, this might be the only time in the universe when we will see particles coming from the farthest distance. After that, our cosmic horizon will become so small that even if we wait an infinite amount of time, we will never be able to observe photons or other particles coming from beyond. Before we reach that definitive distance, we need to understand a bit more about the CMB radiation. According to scientists, it is believed that this radiation was emitted about 13.7 billion years ago, approximately 380,000 years after the Big Bang, from a hot hydrogen plasma when the universe was cooling down. Today, this radiation is in a state of continuous movement, about 46.5 billion light-years away from us, due to the expansion of the universe. But how is it possible when the universe itself is only 13.8 billion years old? How can we observe CMB radiation coming from 46 billion light-years away? Since the formation of the universe, it has expanded rapidly. When, a few million years after the formation of the universe, CMB radiation was being emitted, the size of the universe was almost 1,100 times smaller than today. For this reason, at that time, the objects present in the universe, mainly hydrogen clouds, were very close to each other. When the photons of CMB radiation were emitted from the primordial hydrogen plasma, they were only 42 million light-years away from the gas clouds that would eventually form the Milky Way and Earth in the future. Although the distance was not too great on a cosmological scale, at that time the universe was expanding rapidly, and along with it, the wavelength of the CMB photons was increasing. So, when this radiation finally reached Earth, after 13.7 billion years, their wavelength had increased by 1,210% compared to when they were emitted, and the universe had become larger than its past size. During this period, the plasma clouds from which the CMB radiation was emitted have now reached a distance of 46.5 billion light-years due to the expansion of the universe. And by now, they must have also undergone the formation of galaxies and stars that we will never be able to observe in the future because, due to the expansion of the universe, their current light will never be able to enter our Hubble sphere. Now let's take a look at an example to understand this more deeply. Imagine you are standing in a large hall with several doors. Now, if you turn on the light in the hall, you will see that the light easily reaches all the doors. Now let's suppose that suddenly the floor of the hall starts expanding in all directions at the speed of light. In this case, the distance between the doors and the light source is also increasing rapidly. But since the light photons were already very close to the doors from the beginning, despite the increasing distance, they easily reach the doors. Here is the twist. While the past photons managed to reach the doors along with the expanding corridor, the photons currently emitted from the light source will never be able to reach the doors across this expanding corridor due to their fixed speed. This is the phenomenon we are witnessing in the universe. Therefore, for the photons that had already reached the region of space where the Milky Way and Earth are currently located, it was easy to reach Earth, because the rate of expansion of the universe in this region is slower compared to other parts of the universe due to the gravitational pull of the Milky Way. There is also a spherical horizon around Earth that covers almost 14 billion light-years, known as the Hubble horizon, where the expansion speed of the universe is slower. For this reason, the light from objects within this horizon can reach Earth. In fact, objects located outside this horizon cannot enter due to the rapid expansion of the universe at the speed of light. This means that, according to the current cosmological model of the universe, the early universe plays an interesting role, because at that time the volume of the universe was so small that the gravity of the mass present in the universe slowed down the expansion of the universe for a short period. However, dark energy soon overcame gravity, and the universe began to expand at a speed many times greater than the speed of light. But during that brief window of slow expansion, many particles had already entered our Hubble sphere, including the CMB radiation, which is also beneficial for us because if this had not happened, we would never have been able to prove the Big Bang theory. This would have led us to not understand the basic fundamentals of the universe even today and to be perplexed about how the formation of the universe occurred. Now let's move on to our last question. What is the absolute horizon point of the universe where even future light can be captured by us, and beyond which, we will never be able to capture light? As we learned a little while ago, currently, the radius of our cosmic horizon sphere is about 46.5 billion light-years. However, in the future, in about 10 billion years, this limit will increase by about 33%, reaching almost 61 billion light-years. At that time, our actual observable universe will extend to a diameter of about 122 billion light-years. Obviously, the universe will extend even further beyond that moment, but for humans, this will be our future absolute limit. We will only be able to see objects within it, and there will be a horizon point so far that, no matter how long we wait, we will never receive light or signals beyond that point, even if we wait an infinite amount of time. If you look beyond the galaxy at that moment, you would feel quite empty, because by then even the galaxies around us would have moved so far that seeing them in visible light would be almost impossible. Therefore, the light that would reach Earth at that time would mainly be in the form of radio waves, with wavelengths so large that even capturing them would require a powerful telescope, spanning billions of light-years. After almost 100 billion years, the universe will finally be completely immersed in darkness, because due to the expansion of the universe, our Hubble horizon will shrink and remain limited only to our galaxy. For us, the entire universe will be confined to just the Milky Way, or perhaps I should say Milkometa, as the light from beyond will never reach us again. This means it will no longer be possible for us to search for aliens in the galaxies of our neighbors through telescopes. By the way, what do you think about this? Have you ever imagined that there will be a time when we will no longer be able to see the universe beyond our galaxy? If so, let me know in the comments below, leave a like, and subscribe to the channel. See you in the next video.